Time for a pop quiz. QED.
Hi, everyone, and welcome on in. My name is Penn Center. We're here today for lesson number 4, lecture number 4 in the linear algebra series. Martin with the snag. Nicely done, Martin. Hi, Mr. Aldrich. Welcome in. Hope you're doing well on this lovely Saturday morning. Now we're just going to wait a few more seconds for the ads to roll on through, and that way we don't have any pre-roll ads. During our first hour of presentation, we're going to be joined today by Gumboy. We're going to be talking a little bit about linear transformations and I think some of the properties and consequences of linear transformations. That's kind of the avenue that we're going to be kind of walking down for the next couple of lessons. So I'm actually pretty excited. This is a fun little topic of exploration. So. Oh, the golden kappa! Wow, where'd you sneak that one out of? Oh, congrats on the golden kappa snag, Martin. Okay, we're gonna bounce over into Discord, get set up with Gumboy, and we'll get this show on the road. Good morning, happy Saturday, everyone, or Sunday for some of you potentially. Thanks so much for coming and hanging out with us. So we're gonna start lesson 4 here. It's gonna be kind of our start into the discussion about linear transformations and some of their consequences. So I'm super excited for Gumboy to take over the reins here. You're very excited to talk about linear transformation, so I will let the floor be yours. I'm going to go just on mute. I'll be monitoring the chat both in Discord and on Twitch, and if I need to, I'll jump in and have you answer any questions. All right?
Thank you. How's everybody doing today? My name's Gumboy. I am a math graduate from UC San Diego from 2021. I've been working the past couple years as a math teacher doing middle school, high school math, and linear algebra is one of my all-time favorite subjects. I was able to TA for a couple of classes back when I was an undergraduate, and I'm very excited to talk about probably one of the most important ideas when it comes to vector spaces. So kind of just as a little bit of a rundown for how we're gonna go about things today. We're gonna start off with just like basic definitions, whole ton of examples. We're going to go through some of like the basic properties of like what does a linear transformation do. We're going to go into the null space and the range as two very important subspaces whenever we have a linear transformation going on. And then we're going to end things off by talking about matrix representations of a linear transformation, which is what allows us to do a lot of computational stuff whenever we have a linear transformation going on. And if y'all are ready, I'm ready. So what have we done so far? We first went through what is a vector space? What is a subspace? Very basic groundwork for just like what are the structures that we are discussing in general. Then we took a turn into, okay, how do we play around with the elements in a vector space? We talked about linear combinations, we talked about spanning sets. Then we've gone into linear dependence, linear independence. Whenever we have a linear combination, like do those work independently of each other, or do they really kind of collapse in on themselves whenever we play around with them together? And then finally, we talked about probably like one of the most important ideas whenever you have a vector space by itself is the idea of a basis and dimension of a vector space. So really what we've done in this first chapter is just talk about vector spaces in and of themselves. How do they talk to each other? How do we talk about the communication between any two vector spaces and how they interact with one another? How can we talk about the relationship between any two vector spaces? And if we think back to how do sets play around with each other, that's through the language of functions. Functions describe the world. And during my collection and during my research for making up these slides, I found just the perfect video to show this, and I want to show off this 30-second video of a math professor for y'all. 46 seconds, I lied, whoopsie. I'm just gonna let him take the floor.
Functions describe the world. Everything is described by functions. The sound of my voice on your eardrum, function. The light that's kind of hitting your eyeballs right now, function. The entries you put in your random matrices, function. It's all function. Different classes in mathematics, different areas in mathematics study different kinds of function. High school math studies second degree one variable polynomials. Calculus studies smooth one variable functions. And it goes on and on. Functions describe the world.
I hope that got the point across. Really, functions are one of the major things behind functions is that it allows us to talk about relationships. Whenever we're making a relationship between two things, usually we have a function. Whenever we're doing operations, so like adding, subtracting vectors, multiplying by a scalar, we're dealing with functions. Whenever we're talking about just the structure of things, we can analyze it using functions. Whenever you do kind of anything, you have a function. So really our question is, what kind of functions should we be looking at when we're talking about vector spaces, given that we have all of this nice structure that we've defined on a vector space? And really a lot of what we're doing today, if you ever go on to study any abstract algebra, so perhaps if you're in the art and reading group in our simple group Discord here, you'll see this with groups, you'll see this when we get to rings, you'll see this with fields in particular. We talk about very specific types of functions for fields. Whenever you talk about, if you ever get into modules, if you get into anything really, we want to talk about functions that preserve a specific type of structure. So what would we want functions to do between vector spaces? Well, the two things that we have going on with vector spaces are that we have vector addition. So ideally, we want a function to preserve that vector addition. And we want it to preserve scalar multiplication. So we can multiply any vector by a scalar in our base field. So we wanted to preserve that idea of, okay, if I'm multiplying by a scalar in one vector space, I'm multiplying by a scalar in another vector space. And it turns out if I just focus on these two things, then a lot of other stuff will come from it. So let's try to workshop a definition of what kind of functions we want to look at. So let's say we have two vector spaces v and w over some common field f. Let's take a look at what kind of functions t going from v to w such that t has to preserve vector addition and t preserves scalar multiplication. So if I'm preserving vector addition here, then what I basically want to say is if I've got addition going on right here in v, then I want addition going on right here in w. So if I have addition going on in my domain, I want addition going on in my codomain. And so the way we could talk about this is if I have any two vectors v and w in my vector space v, then applying t to the sum gives me the sum of the outputs. So applying it to the sum gives me sum of outputs. So t of v plus w equals t of v plus t of w for all v and w inside my vector space v. Now, if we're talking about scalar multiplication, well, we can kind of think of it in the same way. And this is kind of why we want to define v and w over a common field f, so that multiplication by a scalar makes sense and we don't have to apply any sort of change to the scalar in question. So the way we could think of this is if I'm multiplying my vector v inside of my domain big V by some scalar lambda, then it's the same as multiplying the output by that scalar lambda, no matter what my choice of input is for all v and v, and whatever my choice of scalar is for all lambda in f. So this is kind of what we want to talk about whenever we're talking about preserving vector addition and scalar multiplication. And this is going to lead into like our big boy definition here. If we have v and w being vector spaces over a common field f, a linear transformation is a function t from v to w such that, first up, we have that t of v plus w equals t of v plus t of w for all v, w, and v. And then t of lambda times v is equal to lambda times t of v for any choice of vector v in our domain and any choice of scalar lambda in f. If I want to compactify this definition, turns out to be equivalent, I could say that for any choice of v and w in my domain and any choice of scalar lambda, if I have that t of lambda v plus w is equal to lambda times t of v plus t of w. I want to leave this up for a second to kind of soak in this definition, because really everything we are doing today relies on this definition here. Any questions on the definition so far that I can go ahead and answer? I'm seeing from Kirby, what if lambda isn't in a field? What are you meaning right there? Just to kind of clarify that question. So to answer the idea of, well, we want to talk about the idea of preserving scalar multiplication. And really, whenever we have a vector space, we have this idea that we can multiply by any sort of scalar living in a field kind of above us. And that's really how vector spaces are defined. So if we're not having that lambdas like inside some field structure. And I think we're dealing with like a different structure than a vector space entirely. So like we really can't like define lambda times v without like defining some sort of structure. And then to kind of respond to Vungaskin, we have the fields that v and w are defined on be isomorphic. I believe we can. The only issue with that is that we'd have to also define a mapping or use a function between the fields. And so we probably get like, if I have t as my map from v to w, I need another map like f going between my fields like f and let's say g. And I want, that is an ugly f. And I would want my function f right here in order to probably like preserve properties as well. And we'd probably end up getting that this step right here, this t of lambda v equals lambda times t of v, to be like t of lambda v equals f of lambda times t of v, which like can work a little too above what we're wanting to talk about today at the very least. So like to keep things simple, to keep things just compact, we're going to assume that they're over the same field. And here is where I want to get into a bunch of examples to get an idea of, well, what do these look like? What are a bunch of examples of this? So I'm going to run through and kind of give the vibes of why are all of these linear transformations. And at the very end, I'm going to give a funky example that we're going to prove together is an actual linear transformation. So let's start with bare bones basics. These three pop up a whole bunch of times as like simple cases, and having these in our toolbox is useful. So testing claims, we can use these to like show counter examples as just to have stuff in our toolbox. So if you have any two vector spaces v and w over some scalar field f, we can define the zero map, which sends everything in w to the zero element of every element of v to the zero element of w. So we're just forcing everything in v to be shoved down to zero. And this kind of trivially works as a linear transformation, because if you add 0 to itself, you still get 0. And if you multiply any scalar by 0, you're going to get 0 again. As our next kind of simple example, we have what's called the identity map. And just for any vector space v, this is the map that sends any element in v to itself. So I keep on saying trivially. I'm probably going to say this like a good amount this talk. The identity map is going to preserve addition, because if I have v plus w, the identity map will send it to v plus w. And if I do lambda times v, the identity map is going to send it to lambda times v. Friedberg uses the notation of I sub v for the identity map. I see ID of v a lot in other fields of math, in like all sorts of other fields of math, because the identity map is a very useful thing for a lot of different subfields, especially when you're dealing with this structure. And then finally, is another simple example. Whenever we have a subspace, we can restrict the identity map down to where the domain is only considering elements of this subspace. So if I have a subspace U of a vector space V, I can talk about the inclusion map. This symbol right here is the Greek letter iota. So I-O-T-A, which basically sends the element in U to its copy in V. Since U is a subspace, it acts as its own vector space, and it has the same definition of addition and scalar multiplication as V does. So really, this is a more specialized case of the identity map, and it works in the exact same way. So these three are just very simple examples of linear transformations that I like to have in my back pocket. To go off of slender. Dot product is also a linear transformation, right? It is actually an example of what we call a bilinear transformation. So like if I restrict one of my inputs, then it's linear in the other input. Yeah, I believe Friedberg goes into that in a later chapter, so that'll be for the future when we get into that. But yes, it is an example of a linear transformation. So let's talk about matrices, because that was also a pretty big point of what we talked about in the first chapter. So I'm going to given a field F, we're going to have M sub M times N of F be the vector space of all M by N matrices with entries in F. So in the last chapter, you talked about something called the transpose, where the transpose swaps the rows and columns of any matrix. So if I have that if I look at the ith row, jth column of the transpose of my matrix, that's the same as the entry from the jth row and ith column of my original matrix. If I take a look at this transpose as a function, then I've got a linear transformation going from the set of all M by N matrices to the set of all N by M matrices. So swapping around rows and columns like that, like how the transpose does, defines a linear transformation between two different spaces of matrices. And if I have that they're all square matrices, then it defines a linear transformation from the set of square matrices of size n by n to itself. Following up on that, in Friedberg chapter 1, they also talked about the trace of a matrix, which is the sum of all the diagonal elements of a matrix. And if I define a map TR, this defines a linear transformation going from the set of all n by n matrices. I have to specifically make sure that it's square to really talk about the diagonal matrices like proper, or diagonal entries properly. You could, if you wanted to, do it for m by n, but you wouldn't be getting like a proper diagonal through a matrix. You would have to be cut off at some point. Then this map is a linear transformation from square matrices to the base field. And the reason why our codomain is the base field is because we are dealing with, that is a little too thick right there. Because we are dealing with a sum of scalars technically. So these two maps are really useful for whenever we're talking about matrices and going back and talking about this assignment of stuff that we've already studied and thinking about it as like I'm assigning to this matrix this other object, whether it be another matrix or a scalar. These define functions, and it turns out because they preserve addition and scalar multiplication, they turn out to be linear transformations as well. Now, this is a part that isn't really talked too much in depth in Friedberg, but I like these little examples to play around with. So if I have a scalar field F, I want to discuss the vector space of infinite sequences, and I'm going to call it F infinity. So when I say an infinite sequence, you can think of it as an infinite ordered list of, let's say, like A1, A2, so on and so forth up until forever. And all of these entries here are elements of my base field. So this is a vector space if I define addition element-wise. So if I did A1, A2 dot 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 plus B1, B2 dot dot dot, then vector addition in this space would be, okay, I'm adding my first coordinates together. I'm adding my second coordinates together. I'm adding like my ith coordinates together. And then scalar multiplication would be, okay, I multiply every single coordinate by whatever scalar I pick from my base field. And this defines a vector space structure on these infinite sequences. So the first map I want to talk about is what we call the right shift map. So if I have a function S that goes from space of infinite sequences to itself, the way it works is I shift all of my coordinates to the right, and in place of my first coordinate, I add 0, which comes from the field itself. So this defines a linear transformation because all of my elements in my output are still going to be sums. If I'm adding like x1, x2, x3 to like y1, y2, y3, so on. 0 is still going to be chill because 0 plus 0 is 0. And then I can split up those remaining coordinates into like the sum of its pieces. And the same idea holds if I multiply everything by a scalar. A scalar times 0 is equal to 0, so it doesn't really change anything. And then subsequently, we have a right shift map. We also have a left shift map, which we denote by S star. And the way that this works is we shift everything to the left, meaning we delete this first coordinate right here, and we're left with the sequence of everything else. And this similarly also defines a linear transformation because addition and scalar multiplication are still preserved in these pieces. It doesn't really matter what this first coordinate is. And so these are two linear transformations I like when we're dealing with infinite sequences. These are used in particular in functional analysis, where you're talking about space, infinite dimensional vector spaces. So let's get a little meta. Let's talk about functions. So let's say we have a set S and a field F. I'm going to let F, curly F right here, fancy F, of SF. This is going to be the set of all functions going from my set S to my field F. There's a vector space structure on this set by defining F plus G of S to equal basically the sum of my outputs. So F plus G of S is equal to F of S plus G of S. I can talk about this addition because my codomain is a field. So I can define addition between any of the outputs properly. And then the same idea, I can define if I have any scalar lambda that lives in F, I can define lambda of F of S to just be the function where it equals lambda times the output for F. And this works as well because F of S, again, is in my field. That defines a proper vector space structure on my set of functions. So if I have some fixed element, I'm calling it little s, we're going to talk about what's called the evaluation map. So this is the function where I take any function between my original set and my field. My output lives in this base field. And basically what I'm doing is I'm taking any function that lives in here and I'm evaluating it at the element that I've chose. So in other words, I'm calling it epsilon sub s. So epsilon sub s of f is equal to f of s. So my output, I am forcing my original function to be evaluated at this base point that I chose. And this defines a linear transformation just because of how the vector space structure works on F. It takes a little bit of just like formal definition pushing in order to like formally prove that this is a linear transformation, but really it just comes from like how do we define the vector space structure on my set of functions. To be a little bit more expansive in our world, if I have subsets, or if I have A, which is a subset of another set B, then if I have a function going from B to F, I can define a new function by restricting all of my inputs to live in A. And we call this F. I don't know if there's a specific name for the restriction, but I just call it like F restricted to A. So rather than talking about all of my possible inputs that live in B, I can discuss my function where I'm only thinking about inputting stuff that comes from A. And this properly works because A lives inside of B. It could be the same, but it could also be smaller, but it does live inside of B. This restriction itself defines a linear transformation. This defines a linear transformation from the set of all functions going from B to F to the set of all functions going from A to F. So by considering this restriction map, I'm creating from a function going from B to F, I can create a new function that goes from A to F. And again, this is linear because of the vector space structure we defined on the set of all functions going from a set to a field. I know that this is very higher up in terms of examples, so I want to take a little bit of time to just make sure. Does anybody have any questions, comments, concerns on anything from this slide in particular? And yes, to answer Slender's question, linear map is another. I'm using it interchangeably between linear transformation, linear map. Yes, F has to be the same field. I'm fixing like the same field for this. If I were to do different fields, off the top of my head, I would have to play around with like how the definition works, but I feel like there would have to be a map going between the fields in order for it to properly work. I see a question from above. Is shifting transformation for a sequence would be... Okay, yeah, we talked about it. FB to FA of F is a map from a function to another. Yeah, so we're going from a set of functions to another set of functions. My input itself is a function and my output is another function. So we've got a little bit of meta-ness when we're talking about this, but really at the end of the day, these are still sets. We still have elements and we're still playing around with them in the same way. I think that's a map from a vector space of functions to another. Exactly. Yeah, you got it right, Slender. Yeah. So I'm going from a vector space where the vectors themselves are functions to another set where the vector space where the elements themselves are functions. So here our vectors aren't really vectors in the traditional geometric way we're thinking about them. They just play nicely with addition, scalar multiplication. Okay. So let's move on to, now I want to go through a quick like rundown of here's examples where if you've taken calculus or if you've taken statistics, you should be very familiar with these. So I'm going to denote C or C0 of R is the set of all continuous functions from the reals to themselves. If it, hopefully people recognize this Blackboard bold R. This is the set of all real numbers. So if I'm fixing a real number A, if I take the limit as a function approaches this input of A, this is a linear process. So this defines a map from the vector space of all continuous functions to the real numbers, where my input is a function, a continuous function, and my output is the limit as x approaches A of f of x. And hopefully you remember from your studies of calculus, if someone hasn't taken calculus here, this is perfectly fine. You can just kind of gloss over this. The limit is linear, meaning the limit of a sum of functions is the sum of the limits. And then if I'm scaling a function by another real number, then the limit of the scaled function is the scaled limit. Going on from limits, we have the derivative. So just to kind of be nice, you can be a little bit more expansive with your with your input. But I'm going to let C1 is the set of all functions with a continuous derivative. So if I'm taking the derivative of a function, then this defines a linear function transformation, where I'm sending this continuously different function with a continuous derivative to the derivative itself. Or if I want to use my Leibniz notation like I'm doing right here, I'm sending f to df dx. And hopefully it's clear that this is linear, knowing that the derivative of a sum of functions is the sum of the derivatives, and then the derivative of a scaled function is the scaled derivative. Alternatively, another way you can see it, the derivative is defined based on a limit, and we have just seen that the limit function itself is a linear transformation, so this specified limit should also be a linear transformation. So after that, we talked about limits, we talked about derivatives, let's talk about integrals. If I have a continuous function, then I can define a linear transformation from the set of all continuous functions to the real numbers, where I'm sending this function f to the integral from a to b of f of x dx. And here I'm assuming that a is less than b. If I had a was greater than b, then technically I would just have, it would go from negative b to negative integral from b to a. No problem in defining that. And if they were equal, this would just turn into 0, which that's just the 0 map that we talked about earlier. Integrals are linear. You can split integrals over sums, and if you're multiplying a function by a scalar, you can pop it right out. And then finally, this is coming from statistics. Here, if you haven't taken statistics, this is perfectly fine. I'm going to let rand of omega be the vector space of all random variables on some sample space omega. If I'm taking the expected value of a random variable, this is a linear transformation. The expected value you can think of as like a generalization of the mean, if you've seen like basic statistics before. It turns out if I'm taking the expected value, then if I do the expected value of the sum of two random variables, that's the sum of the expected values. And then if I scale a random variable and take its expected value, then that is equal to the scaled expected value. So that was the sum right there. And then if I do the expected value of, let's say, like lambda times this random variable x, that's equal to lambda times the expected value of x. So a lot of processes that we are familiar with happen to be linear because they preserve sums and they preserve multiplication by scalars. I'm going to take a little bit of time to look at questions again. So to answer Slender's question, if I want to take the second derivative, you can think of that as, we're going to get a little bit more into composition of linear transformations in our next presentation. I believe that's section 2.3 in the book. But really, if you, spoiler alert, if you take the composition of two linear transformations, it's also a linear transformation. So really, the second derivative is just doing the derivative and doing it again. So the derivative also would go from C2 over to C1, and then doing that again would go to C0, so you're defining a map from C2 over to C0. I do like this question, other question from Slender though. What are the advantages of classifying these types of functions maps as a linear map or linear transformation? If it's linear, and we know that there's a vector space structure, we can apply linear algebra to our scenario. So if you've taken like multivariable calculus, for example, you probably would have seen the Jacobian and the Hessian. Those are defined based off of matrices and determinants. And those are very important to the study of like these multivariable derivatives. So the fact that we can talk about it through the lens of linear algebra just gives us more tools in our toolbox. I don't see any other questions going on. I'm going to take like a little bit of time to let this run through and answer like this final question. And then we're going to finally move on to kind of like formally proving that something is a linear transformation. So this gives my okay. I'm going to move on to the next slide here. So I'm going to introduce a brand new vector space structure that we have not really seen before. It acts a little funkily, but I like this example. I think it's cute. I think it's another way of thinking about how addition and multiplication don't really necessarily need to act like traditional addition or traditional multiplication. So hopefully from algebra pre-calculus classes before, you've seen this interval notation. So I'm considering the interval of all positive real numbers, so the ray going from 0 to infinity. I'm going to define a very funky vector space structure on this set. So if I have two positive real numbers, I'm going to define the addition between them. I'm denoting it by this, what we call O plus, just to show that it's not really addition, but to show like, hey, this is addition in our vector space that we're defining. Is that vector addition with the positive real numbers is really just multiplication. If I have two positive real numbers, I multiply them together, I'm going to get a positive real number. I can't make it equal to 0. It's going to be strictly positive. And then if I have any real number r or x in the set of all real numbers, then scalar multiplication is actually going to be exponentiation. So if I do x, and then this is what we call O dot. So if I do x times this positive real number a, I'm going to have that be equal to a to the power of x. And the reason why this is positive, if I think about the exponential function and I take a look at its graph, the range of this function is the positive real numbers. It may look like this if a is greater than 1. If a is between 0 and 1, the graph is going to look like this, but still doesn't change the fact that the range is all positive real numbers. So this is forced to be a positive real number. So through the properties of just like multiplication and exponentiation, this defines a very funky vector space over the positive real numbers. I don't want to go too much in depth into why this is a vector space, because I really want to focus on linear transformation. So I'm going to leave this as an exercise to all of you at home to prove that this actually does make a vector space over the real numbers. I want to focus on the idea that we can define a linear transformation from these positive reals with this funky vector space structure to the regular real numbers as just like a field. The natural logarithm defines a linear transformation between these two vector spaces. So let's get into the why. So the natural logarithm preserves vector addition because it turns multiplication into addition. So vector addition in our new vector space is multiplication. So ln of a o plus b, that's the same as ln of a times b. This turns into ln of a plus ln of b. And this is specifically addition between two regular real numbers. And we also have that the natural logarithm turns exponentiation into multiplication. So if I have the natural log of x times a in my funky vector space, that's ln of a to the power of x. I take that exponent, yank it in front, and I get x times ln of a. So what's going on is that the natural logarithm turns my funky vector space structure into regular scalar multiplication, regular scalar addition in the real numbers. And so as another little exercise, and this kind of leads into a little bit of what we're going to talk about next time, which is composition and isomorphisms. The inverse of this map is the exponential map. And I want y'all at home to show that the exponential map defines a linear transformation from my regular reals to my positive reals with this funky vector space transformation. Looking in the chat. Single dimensional problems to as many dimensions. So you only need to. Yeah. So like as I was describing earlier, so vector addition in the positive reals is regular multiplication within the real numbers, and then vector or scalar multiplication is exponentiation as it works in the real numbers. So like this numerical multiplication, even though it's multiplication, is what we consider to be our vector addition. And then this exponentiation is our scalar multiplication. I like this example just because it kind of twists and plays with your idea that like vector addition you would think of as addition, and then multiplication is what you think of as multiplication. So we're kind of flipping it on its head, and we're talking about multiplication and exponentiation, which both are kind of defined based off of multiplication, which again kind of throws our idea of like what is addition really? Yeah, we are saying that like A times B is like we're doing A plus A plus A plus A B times. This gets a little funky once we start talking about like, well, what if like B is 1/2? Because that perfectly fits in here. But like if we're doing like, I don't know, like 2O plus 3, we have that idea. But this kind of breaks if I did, well, okay, what if I did 2O plus pi, for example? This is what I'm leaving as kind of an exercise to play around. It's if I this is why I'm showing off this example. Addition doesn't necessarily have to be addition in the traditional sense, but it works in the same way that we want it to. So like this is commutative, this is associative. We have an identity, we have an additive identity, we have an additive inverse. Scalar multiplication is also associative. We have, what else was I about to say? We have that this is distributive. Yeah, I am casually calling multiplication equals addition. I'm saying that this I'm saying that this real number multiplication is my vector addition. I'm saying that this exponentiation is my scalar multiplication. Yeah, and I'm going to kind of leave it there as like a challenge to all of you at home. And this here is why I like this example. So let's talk about very basic properties. We're not going to go too much into the proofs of these, but I want to talk about them a little bit. So let's say we have two vector spaces over a common field F, and I have T as my linear transformation from V to W. So the first thing we have is that any linear transformation preserves 0. So if I have my 0 element in V, that maps to the 0 element in W. So the reason why this works is if I do T, I'm going to drop the V just so I don't have to write that much. T of 0 plus 0, well, if I split it up over addition, I get T of 0 plus T of 0. But on the other hand, 0 plus 0 in my domain is just T of 0. So I have one copy over here, two copies over here, subtract one from both sides, I get that the single one that I'm left with is 0. So next up, if I am taking the additive inverse of any element in my domain, then it's going to be the additive inverse in my codomain. And we can kind of get to this by using this property right here. So if I do that same trick from before, where I'm doing like t of v minus v, well, on the one hand, if I split it up over addition, I get t of v plus t of negative v. And on the other hand, this turns into 0, so my output's going to be 0. And so subtract by t of v on both sides, I get my desired equality. And then finally, this is the one I'm going to abuse the most throughout the rest of this chat. If I have a collection of vectors, so like n vectors in V and n scalars in my field F, then I can split a giant linear combination like this up into a linear combination of the images. And this really just comes from like repeated application of my definition. If you want to formally prove this, I would say like use an induction argument. Be like, okay, we know it for the case of like 2. Now if I have a case of n, let's say it holds for like n minus 1 vectors, and then going up to n, I can split it up twice using my regular definition, and then for the n minus 1 vectors it works. There we go. So really the idea is this is going to happen a lot. Usually if it happens for 2 things, it's going to happen for as many finitely many things as you want. And this guy I'm going to use the ever-loving heck out of. Because if I have just a generic linear combination, I can break it up using a linear transformation. And obviously, if I really wanted to, I could have this if I like be the definition of a linear transformation, just any map that does this. So let's talk about bases. We talked about, like, when we talk about linear combinations, we want to usually represent linear combinations of vectors in terms of like a basis of a vector space. So let's say I have this basis v1 through vn, and I've got a linear transformation t from v to w. So if I have any vector in my domain, that's a unique linear combination of my basis vectors vi. So let's say I just have some vector v, and I write it like this. It's the sum from I equals 1 to n of lambda I vi. All my lambdas are scalars. All my vi are my basis vectors specifically. So from what we just discussed, if I apply t to this linear combination, I can break it up in terms of the images. So t of v is equal to the sum from I equals 1 to n of all my lambda I times all of my images of my basis vectors. So really, all of these scalars are determined by my choice of my vector. That means the image of this vector has to be determined by the values that I assign to my basis vectors through this linear transformation. These lambda I are already predetermined when I get my input, so the output has to be determined by all of these guys right here. And this is a really important fact, because really I can construct all of my linear transformations by just determining what happens to my basis vectors. And that's going to lead into our first theorem for today. And this is theorem 2.6 in Friedberg, 4th edition. So if I have 2 vector spaces v and w over f, let's say I have a basis v1 through vn of v. If I have any n vectors in w, so w1 through wn, there exists a unique linear transformation going from v to w such that t of all my basis vectors equals these wi for any choice of n. So the thing I want to really make clear before we jump into the proof is that all of my v's constitute a basis. All of my w's don't necessarily have to. At least for right now. We'll talk about what happens when this is a basis later on, though. So, based on my discussion from before, I'm going to just define it as so. So, if I have some vector v, which is a linear combination of my basis vectors, I'm going to define the image of this v right here to be that same linear combination with my same scalars. But instead of using my v's, I'm using those w's that I picked. So by definition, we're kind of forcing that T of Vi is equal to Wi for all of my choices of I. So the three things I need to show are T is well defined. So basically meaning that like this guy right here can't be sent to two different things. I need to show that T is linear because I want a linear transformation. And then I need to show that T is the only linear transformation that can do this. So those are the three things that I want to get through in order to have my theorem. So let's look at the first thing. So I have specifically a basis of V. All of those scalars, what I'm calling weights, lambda I, are uniquely determined by the vector and by the basis. So all of these scalars are uniquely chosen for any input that I pick. So that means I can't have V be mapped to two different things because then I would have two different sets of scalars, but then my set wouldn't be a basis. So that's why T has to be well defined. Because if I went to two different things, then I wouldn't be a basis. So here, let's assume now we're going into that it's linear. If I have two vectors going on V, I'm letting my scalars for V be alphas, and then for W, I'm letting them be betas, then I'm going to use my compact definition rather than like going through both at the same time. So if I have some scalar lambda and I apply it to V, and then I add W, my scalars are going to be of this form where it's like lambda times all my alpha i's plus all my beta i's, and then times these vectors here. I don't even have to worry about these. So through the distributive property and by splitting up my sums, all my lambda alpha i's get multiplied right here. And then I've got plus all my beta i's, which also get multiplied right here. I can split up my sums and I can factor out this lambda. I get its lambda times my alpha i's times w i's, plus just my regular beta i's times w i's. And lambda here only affects this guy because lambda is only affecting V. So it's only affecting my alpha i's. And so by our definition, this would be the image of V right here. And then this guy right here would be my image of W. And so I've got that this satisfies my compact definition of linearity. So now what I want to show is that this is the only transformation that can do this. So let's say I have another linear transformation I'm going to call it T prime, where T prime also does the same thing. So let's take a look at T prime of V. So because T prime is linear, I have that I can split it up as a linear combination of the images of the basis vectors. So I'm using the idea that V is this giant sum of all my lambda i's times my v i's. So applying T prime to this splits it up like so. Well, I know that because T prime satisfies what I want it to, all of these T prime of VI's by definition have to equal these WI's. But now I've got that T prime of V is the same image as T of V, which is this linear transformation that I defined in the very beginning. And since my input didn't really matter, this works for any input that I shove into it, V isn't specific, that means that T prime and T are the same for any input that I plug in. So they have to be the same function. So now we finally have proven that my function's well defined, my function is linear, and my function is unique. So this allows me to, if I have a basis of my domain, kind of construct any linear transformation that I want by just saying, where do the basis vectors go? So really the main point of this theorem that we have is a linear transformation is defined based on where it's where the basis vectors of my domain go. So to give a little bit of an application to this, let's talk about formally defining a derivative. So we've seen the notation before of P sub n of x being this vector space of all polynomials with indeterminate x. Coefficients in my field, let's say f, and degree of at most n. We've talked about before that there's a very nice basis for this. It's an n plus 1 dimensional vector space where my basis is 1, x squared, all the way up to xn. Without even needing the idea of calculus, I can force a definition of a derivative. So I can go from polynomials of degree n to all my polynomials of degree n minus 1 and define it by just saying what happens to all of my basis vectors. So I'm saying that d of 1, d is my formal derivative map. Constant functions, when you take the derivative, go to 0. So I'm saying d of 1 is equal to 0. And then whenever you have a polynomial, or whenever you have like a power of an indeterminate, you bring the power down and then reduce the power by 1 up top. So d of x to the k is equal to k times x to the k minus 1 for all k between 1 and n. So specifically by using my theorem 2.6, I can define the derivative map formally without even needing the idea of limits. I can just say, well, here's where all the basis vectors go. Now I can extend it to a linear map. And the way that it extends is that d of, I have a formal like polynomial here. This goes from k equals 1 to n of k times a sub k times x to the k minus 1. And this is how we differentiate a polynomial in general. And we have defined a derivative without needing limits whatsoever. Going into the chat, does this approach work only on polynomials, or can we define the derivative for some other functions in this way? If I remember, if I'm thinking correctly, you can have a vector space of what we call trigonometric polynomials. I think that that's going to be like an infinite dimensional space. But as I'm going to show as like a little bit of a preview in a couple slides here, that it does work in the same way. And you can define these formal derivatives like so. Yeah, you're good with the expansion there, Slender, and then Taylor series. The main issue with Taylor series is that those are infinite sums, and whenever you're taking a sum of infinitely many elements, then all of a sudden you are inviting calculus, because the only way you can take a sum of infinitely many things is if you're defining like the limit as this goes to infinity. So this works perfectly for finite sums. Once you get into infinite sums, you have to start like defining formal power series ring. That works too. Yeah, you can also define it for that. And just like defining like formal infinite sums. It gets into, there's a whole bunch of things. For now, we're just going to focus on the finite case because finite cases are easiest. So using this third part of our proof that it's of uniqueness, I can define a very nice corollary. So if I have two vector spaces over a field F, I have a basis for V. If two linear transformations exist such that my first transformation T1 and my second transformation T2 agree on the basis for all of my choices of basis vectors, then they are the same linear transformation. So in other words, if two linear transformations agree on a basis of their domain, they are the same linear transformation. And then as an extension to theorem 2.6, I'm not going to go into the proof of this just because infinite dimensional vector spaces can get very finicky, but we have very similar ideas going on. So if I have an arbitrary basis for a vector space V, an arbitrary set of elements for a vector space W, I can define a unique linear transformation going from V to W, which satisfies the same ideas as before. So even though we have an infinite vector space or infinite dimensional vector space, everything can still be written as a finite linear combination. And that's kind of the important thing, and that's why everything is so similar and works the way that it does. Before I move on from basic properties, do we have any other final questions I can answer? Because now we're going to go into the null space and the range. Going once. Going twice. Sold. Okay, so these ideas are very important in linear algebra and just algebra in general. Like having these guys pop up is very, very, like, it comes up so much that we just we have to talk about it. I'm going to introduce a little bit of notation that I often see more, but I'll also show what the Friedberg notation is. So V and W vector spaces over F, it got a linear transformation. The null space of a linear transformation, this is what we use in linear algebra. Outside of that, we call it the kernel. This is the set of all vectors in my domain which turn into 0 in my codomain. So formally, we have the null space. I'm denoting by ker. Friedberg uses n of t. It's all my vectors v, such that when I map them through t, it equals the 0 element in w. And then the range, or the image, Friedberg uses r of t. I'm doing mt. This is just all of the elements that get mapped to. So like I can, if I have something in my image, then there's something in my domain that gets sent to it. So this is the set of all elements of W, such that I can find something in big V which gets sent to it. We've talked about, you would see range in your discussion of just like functions over a set, or between sets in general. Range and domain, or range is something you see in algebra and pre-calculus classes. So we're bringing it up again because it has very nice structure when we start giving our sets structure, when we start talking about vector spaces. So let's go through some examples of null spaces for different maps. I'm going to go through, our first two are going to be some of our basic maps. So the identity map, if I take the null space of the identity map and the inclusion map, because they're both correlated, it's I say the 0 element, really it's the singleton containing the 0 element. Because if you remember, the identity map and the inclusion map, they preserve all elements and just like map them to themselves. So the only thing that can turn into 0 is 0 itself. On the flip side, if I were to look at the 0 map, the null space of the 0 map is everything in the domain, because everything gets sent to 0 by definition. So I can talk about this for derivatives between polynomials or just derivatives between continuous functions. The null space of the derivative map is the set of all constant functions. So the only way you can get 0 is if your function is constant everywhere. Going to the trace map, the null space of the trace map, remember the trace being the sum of all the diagonal elements of a square matrix. If I'm in the null space, then the sum of those diagonal elements has to sum to 0. So as an example of something that might live inside of the null space, I have this 2x2 matrix here, 1, x, y, -1. No matter what I pick for x, no matter what I pick for y, these two have to sum to 0. So any matrix of this form has a trace of 0. Oh, going off of Slender's, yeah, the kernel or the null space, that you can think of it as like the set of all zeros of the function. Yeah. So like if you're talking about like polynomials as functions, if you're talking about like really like any of your classical functions, if you think about like when is it equal to 0, the set of all of those is what you call your null space. So going into the range of the 0 map is the singleton set, I wrote it this time, containing the 0 element, because everything gets sent to 0. So the only thing that can be mapped to is 0. And then on the flip side, the range of the identity map is all of the, when I say all of the vector space, the identity map sends a vector space to itself. Everything inside of here gets mapped to because I'm not changing what any of the elements are. I don't, as our next example going on to the inclusion map is a little different because our inclusion map is going from a subspace into a larger vector space. So the range or the image of the inclusion map is everything inside of U. We already have that U is a subspace, so everything in U lives in V. The only things I'm getting are stuff that already lives inside of U. So going into the right shift map, remember the right shift map sends an infinite sequence, x1, x2, dot, 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 to all sequences of the form, like 0, x1, x2, dot, dot, dot. Basically, I'm putting 0 as my first entry, and I'm shifting all my other entries to the right. The range of this is all infinite sequences with 0 as the first entry. If I pick anything without 0 in the front, I can't have that because I'm forcing 0 to be in the front as my image. Subsequently, I don't have this as a specific thing, but if you want to talk about the range of the left shift map, that actually turns out to be what we're going to talk about later is called surjective. So the left shift map deletes that first entry and it considers all the rest of it. I can always force a sequence by just saying, I don't know, let's have the first element be 0. And then I have the rest of my sequence that maps to whatever sequence I want. And then finally, range of the trace map is the entire base field. I can force a trace of anything by just taking I don't know, a matrix like so, where it's just x 0, 0, 0. It really doesn't even matter what's in here, but this is an example of a way that I can get a trace of any number that I choose. Any questions on Oh, no, I mean. Yeah, pre-images do pop up. That's a generic function thing. We're not going to discuss it too much in here, or at least the language that I'm using is not pre-imagey, but that's a common function thing in general. So let's talk about another proposition. Theorem 2.1 in the book. I'm kind of going a little out of order for that first section. So if I have a linear transformation, the null space and the range are both subspaces. So in particular, the null space is a subspace of V because the null space is everything in V that maps to 0. And then the range is a subspace of W because the range is every element that gets mapped to in W. So let's start with the null space. So to kind of recap, what we want to show that it's a subspace is that it contains the 0 element, it contains sums, and it contains scalar product or scalar multiples. So by our first proposition, any linear transformation preserves the 0 element. So 0 gets sent to 0, so the kernel or the null space contains 0. If I have 2 elements in my null space, then their sum is preserved, but that's the sum of 0 and 0, which is 0. So the sum is also in my null space. And then finally, for any scalar multiple, or for any scalar lambda and any vector v in my null space, then if I do t of the scalar multiple, that's lambda times 0, which is 0. So it also preserves scalar multiples, so that means my null space is a vector subspace. And then with the range, 0 is in the range because 0 maps to 0. So this is doing stuff with the range is a little finicky, and you just have to be careful with your definitions. So let's say I have two vectors, W1 and W2, in my range. Then that means I can find two vectors, V1 and V2, which map to them. So V1 maps to W1, V2 maps to W2. So if I take the sum of W1 and W2, then that turns out to be the image of the sum of V1 and V2. So that means W1 plus W2 has to also be in the range. And then if I have W in my range, I can find V, which maps to it. For any scalar lambda, lambda times W, that's the image of lambda times V. So lambda times W has to be in the range as well, so it preserves scalar multiples. Our range preserves sums, preserves 0, it's a subspace. So, let's talk about injectivity, and we're going to go into surjectivity in a little. Actually, we're not really going to go into surjectivity. Injectivity is kind of important for the kernel or the null space in particular. So, recap, a function's injective or one-to-one if each element in the range is mapped to only by one element in the domain. So, a common way of thinking of this is if f of a is equal to f of b, then a must be equal to b. So this is kind of like the reverse of my well-defined definition of like, if a is equal to b, then f of a is equal to f of b. Another way you can think of injectivity, that's a common definition, but this is usually more useful for like proving injectivity, which is the contrapositive. We get that if a is equal to b, or not equal to b, then f of a can't be equal to f of b. This is the more intuitive way of thinking about it, but this is way more useful for proving things. So, if a linear transformation is injective, the only thing that can map to the 0 element has to be the 0 element. Because we know that the 0 element maps to the 0 element in my codomain. So that means if my linear transformation is injective, then that's the only thing that can map to the 0 element. And it turns out it also works the other way around. So what we're going to prove next is so if I have a linear transformation, T is injective if and only if the null space is just the 0 element of my domain. So we proved kind of the forward implication. So like T is injective, then the null space is just the 0 element. So now we're going to prove the reverse. So if T is injective, the only element that can map to the 0 element in W is the 0 element in V. We just showed that. So now let's say that the 0 element is the only thing in the null space. Let's say that T of V is equal to T of W. Then if I subtract the two entries, then I get that it preserves subtraction as well. We didn't really talk about this too much, but we talked about that any linear transformation preserves additive inverses. So I'm kind of like using this implicitly in order to say it preserves subtraction. But if we know that T of V is equal to T of W, then this entry right here has to be the 0 element. But then I've got something right here that maps to the 0 element. And if I'm assuming that my null space is what we call trivial, then this has to equal the 0 element. So that means they're equal. And that proves that T has to be injective. So let's do a little bit of examples with injectivity in the null space. So the null space of the right shift map is exactly the set containing the sequence of all zeros. So the right shift map, as we talked about before, is I'm deleting that first entry and then scooting everything to the left. Yeah, this should be the left shift map, not the right shift map, excuse me. So if I'm scooting everything to the left, in order for the image to be zeros, oh wait, no, never mind, I mixed it up. I apologize, everybody. We are talking about the right shift map. So we're scooting everything to the right and adding a 0 in the front. So if I've got x1, so on, so on, so on, then I'd be getting 0 in the front, x1, bop, bop, bop. The only way for this guy to be zeros is if everything above it is all zeros. But that means this guy has to be all zeros. So this has to be injective. The null space is just the sequence of all zeros. So my right shift map is injective. However, we take a look at the left shift map, our null space is the set of all sequences of this form, where it's like something followed by all zeros. This can be anything we want, and we're going to get rid of it later on. So this can't be an injective map, because we get a bunch of stuff that maps to 0. We have infinitely many things that map to 0. Responding to slender or right shift maps and left shift maps important. I like them as play examples. They're more useful in functional analysis, but they're fun examples to play around with because I feel like the definition is pretty simple, and I'm using them mostly as just like, let's apply our knowledge to a linear transformation that we know about, and that is pretty reasonable to play with. Cool. So let's talk about the range. Let's talk about bases. So if I have a basis for a vector space, linear transformations on that vector space are uniquely defined by the images of the basis vectors. We talked about that in a previous proposition theorem. So if I have a basis of V, then any element in V can be written as a linear combination of my basis vectors uniquely. And so applying T to it, we've seen this before. All of a sudden now we have a linear combination of the images of my basis vectors. So this leads to actually a very quick proposition. So if I have two vector spaces and I have a linear transformation between them, and I have a basis of my domain, then the range of my linear transformation is exactly the span of the images of my basis vectors of my domain. So, as a very quick proof of this, we've shown kind of in the previous slide that if I have a vector here, it gets mapped to a linear transformation of the images of my basis vectors. So that means the range has to be a subset of the span of all these images, meaning that everything in the image is a linear combination of the images of my basis vectors. So kind of by default, all these T of VI's is in the range, no matter like what it is. And we just proved that the range is a subspace, so it preserves linear combinations. So anything in my span is an element of my range. But since there's this dual inclusion, they are the same set. And so I'm leaving it as an exercise to all of us or everybody at home, do I specifically need this to be a basis of my domain? Do I necessarily need a basis of my domain in order for this result to hold? So that'll be an exercise for the future. And I want to talk about applying this to an example. Let's look at our derivative map. So I'm specifically looking at just the derivatives for polynomials, because these are finite dimensional vector spaces I can play with. A basis for my second degree polynomials is 1x squared. So if I look at the range of the derivative map, then 1 goes to 0, x goes to 1, x squared becomes 2x. And if you have 0 in a set, that doesn't really do anything to your linear combination, so I can kind of axe that. And this would be the same as just the span of 1 and actually x. Because if I have anything going on with 2x, I can just multiply by 1/2 and then get the span of, like, I can just get like x out of anything. So specifically, this is a basis of p sub 1. So all of my linear polynomials. This actually kind of shows that This is what we call a surjective map or an onto map, meaning that the range of my derivative map is my codomain itself. The codomain and the range are the same thing. And again, as another exercise, show that this holds in general. It's just a very nice extension of what I just showed right here. So now we have that the null space, the range are subspaces. Let's talk about dimension. So if I have a linear transformation, the dimension of the range is what we call the rank of the linear transformation. So the rank of a linear transformation is the dimension of the range. And then similarly, the dimension of the null space is what we call the nullity of the linear transformation. So thinking about the null space and the range side by side, we have a little bit of like a dual relationship going on. So if I have a big null space, my range gets smaller because I have more things going to 0, so I have less things that can go to non-zero elements. And then vice versa. If I have a big range, then I have a small null space. If I have a bunch of things going to non-zero things, I have less things that go to 0. So the question I want to pose is, if I know how much room the null space takes up, how much room would the range take up? And when I say that, it's really, if I know the nullity, do I know the rank? And then vice versa. If I know the rank, do I know the nullity? So let's run through some things. So let's start with a base case. If I have a linear transformation T, let's say the dimension of my domain is n. So if I have the kernel or the null space, this is a subspace of V. The nullity has to be at most n. We can't exceed the dimension of our domain. So let's assume that my entire linear transformation is like the nullity is equal to n. That means the kernel or the null space has to be all of my domain. So in other words, this is the 0 map. So that means the rank of the 0 map is 0 because the image is just 0. And if you remember, the dimension of the 0 subspace is 0. Okay, what if the nullity is 0? That means the kernel has to be the singleton containing 0. I know the image of a basis of V is a spanning set of the image. So I know that the rank of T is at most n. So no basis vector can be sent to 0 because I know that the kernel or the null space is just the 0 element. The only way that the rank is strictly less than n is if the image is a linearly dependent set. So let's see what happens. Let's say I've got a basis and I want to see, like, okay, what happens if it is linearly dependent? So this would imply that I can find some lambda i's so that when I multiply with my images, I get the 0 vector. Since T is linear, I can expand back outwards and get that T of all of this, of my linear combination, is equal to the 0 vector. But I said earlier that the null space is just the singleton containing the 0 vector. So this on the inside has to be 0. These form a basis. These are linearly independent. So that means all of my scalars have to be 0. But then all of a sudden we have that all of my images have to be linearly independent. So I just formed a basis for my image, meaning that the rank of T is equal to the dimension of my image. So if I have that the null space has a dimension of 0, then my image has a dimension of n. So now what happens if we go in between? So let's say that the rank of T is equal to k, where k is between 0 and n. So this is the dimension of my image. So I meant nullity. Excuse me, I did not mean to write that. So let's assume that the nullity is equal to k. I'm putting null. Nullity is usually what's written. So I can construct a basis v1 through vk for my null space. I can extend this into a basis for all of v because, again, my null space is a subspace. Hopefully you remember that if I have a linearly independent set, it can be turned into a basis. So these guys are all in my null space. These guys are outside of my null space. These live in strictly V. So none of these new vectors can be in the null space. The image of T is spanned by the image of this basis, as per our proposition from before. But we know that all of these guys right here get sent to 0 because they're a basis of my null space. I have that the image or the range of T has to be the span of everything else that I've constructed. So we know that this is a spanning set. Let's see if they're linearly independent. Well, all of these guys going from k plus 1 to n, if they sum up to 0, then if I were to run backwards, these guys on the inside would have to equal the 0 vector in my domain. But then I know these are all linearly independent because they're part of a basis. If they weren't linearly independent, then I'd be done for. So I'd have that all my lambdas equal to 0 for all of these new k plus 1 through n. This means this is a basis for my range. So the rank is equal to basically everything else. So it's equal to n, which is my dimension for V, minus my rank, or not my rank, my nullity, which is my dimension of my null space. So this proves what we call the rank nullity theorem or the dimension theorem. So if I have a linear transformation between two vector spaces and I have a finite dimension for my domain, then if I add the rank and the nullity, I get the dimension of my domain. So in other words, the dimension of my range plus the dimension of my null space equals the dimension of my total domain. This is a useful fact whenever we're playing with like injectivity, surjectivity. Whenever we have a linear transformation going on, we have this relationship between the kernel and the range. So as a little proposition, as like an application of my rank nullity theorem, let's say I have two finite dimensional vector spaces over the same field, and I have a linear transformation between them. And let's assume that my domain and my codomain have the same dimension. Then the following are equivalent. This is a theorem in Friedberg. I forgot to write that down. Let me go back and look so I can put that up for you. This is theorem, or I have to go back. Oh, this is theorem 2.5. So if I have that these have the same dimension, then the following are equivalent. Basically meaning if I have one, I have the others. So T is injective, T is surjective, and the rank of T is the dimension of V. So using the rank nullity theorem, T is injective if and only if the nullity of T, the dimension of my kernel or my null space, is 0. Because if it's injective, then the only thing that can map to T is injective if and only if the only thing that maps to 0 is 0. And that means the null space has a dimension of 0. If I apply to the rank nullity theorem, this is true if and only if the rank and dimension of V are equal. But we also know that this equals the dimension of W. So if the rank of T and the dimension of W are the same, that's only true if and only if the range of T is equal to all of W, meaning that T is surjective. this is kind of like a quick and dirty application of just saying, like, if I have two vector spaces that are the same in dimension, then if it's injective, that forces it to be surjective as well, which really means it's bijective, if you remember the definition of that. And that basically means the rank of T is equal to the dimension of V, which is more of like a direct application of the rank nullity theorem. So, getting into finally matrix representations. An ordered basis, we need to define a couple of quick things first. So, let's call an ordered basis of a vector space. It's just a basis where I force an order onto it. So I'm assuming that the elements are in some specific order. We have what's called the standard order basis of f to the n. So this is just every n tuple of entries of my base field f, e1 through en. Each of these e sub i's is the column vector with 1 at the ith entry and 0 everywhere else. So for f squared, that is way too thick. My standard basis will look like 1, 0. That's E1, and then 0, 1. So we're going to start defining what's called coordinate vectors. So we know already that any linear combination, or if I have a basis going on, then the linear combinations are unique and the scalars that are picked for it are unique. So I can really define, as I show on the bottom, a linear transformation from V to all of my like n tuples of entries on my field, going from by forcing the each basis vector to go to a part of the standard order basis. So this is why using ordered bases is helpful, because I have it in a specific order. So I'm letting B right here be an ordered basis of a vector space V. If I have a vector V, which is linear, which has a linear combination that looks like this, the coordinate vector of V relative specifically to this ordered basis is, we denote, I'm going to call it V sub B, and we use these brackets. This is the following vector inside of Fn, where it's just, I list out all of my scalars in order from 1 to n. So, quick example, I'm applying it to my polynomial function, my polynomial vector spaces. So let's look at P sub 2. Let's say I take like my basic basis for my polynomials of degree 2 or less. Let's say I take the polynomial x squared minus 2x plus 13. If I'm using my very basic basis, 13 is my top, -2 is my middle, 1 is my bottom, because I'm specifically ordering it as 1 goes first, x goes second, x squared goes third. I could flip it around and give it a different order, and that would flip around my entries in my vector. Perfectly fine. It would just give me different vectors depending on how I order it. If I were to do a different basis, you can verify to yourself that this is also a basis of P2. Then I get something a little different based on the expansion. So if I were to go through and expand it, it turns out I would need 15. So I need 15 times 1. -3, so -3 times 1 plus x. And then 1 times 1 plus x squared. So depending on your choice of basis in general, I feel like that's more obvious than like changing the order. You're going to get a different coordinate vector because you've got a different basis, meaning you have different linear combinations going on. So, if you've taken a standard like lower division undergraduate like linear algebra class where you've talked about a lot of matrix stuff, you'll know that it is very nice to represent a linear transformation as a matrix. And we can define like an assignment based on ordered bases in our domain and our codomain. And this allows us to talk about a lot of computational stuff with matrices. So if I have a linear transformation going from V to W, an ordered basis of V, I'm calling it B1, an ordered basis of W, call it B2, I can force a linear transformation between them by just assigning each element of my first basis to an element of my second. Actually, not even that. I don't even need to assign these to the basis vectors. I can just assign these to whatever. But the idea holds that each of these is an element of W, so I can write it as a linear combination of my ordered basis. So I can take all of these coordinate vectors and mush them together into a matrix. So given a linear transformation and two ordered bases, one of V and one of W, the matrix representation of T in the ordered basis B1, B2, I denote it by T, B1 below, B2 above. This is the M by N matrix whose ith column is T, what happens to T of VI with my ordered basis below. So all of these here are N dimensional. So I've got columns that are N entries long, and I've got M of those. So I'm going to have, never mind, this is N by M. Reverse it. So all of my columns are N entries long, meaning I have N rows, and I've got M of those vectors because I have M of those entries in V. So I'm going to have M columns overall. So quick application of this, and this is going to go into kind of like an example of like how do we apply it. Linear transformations are so useful for computer graphics because a lot of the transformations we want to apply, like rotations, reflections, dilations, happen to be linear transformations. I'm going to focus on this specifically for rotations for this talk, and we're going to talk about it in R2. So let's say I'm wanting to rotate a point XY in my basic like Cartesian plane counterclockwise by an angle theta. I'm going to denote this map by r sub theta. I want to show that this is a linear transformation, and I want to make the matrix representation of this guy. And this gives us, once we start talking about matrix multiplication, a explicit formula. So I'm going to apply some polar coordinates here. If I have a point, xy, I can find the length from the origin to that point, and I can find the angle between that point and the positive x-axis. I can say that, well, x right here is equal to r times cosine of a, and then y is equal to r times sine of a. If I were to rotate by an angle theta, that basically just means I'm taking this angle right here, I'm adding theta to it. So if I were to apply r sub theta and use these polar coordinates, I'd get my image should be r times cosine of alpha plus theta, and then r times sine of alpha plus theta. Expand that using angle sum identities, double cosine minus double sine, alternating sine alpha cosine theta plus, that should be cosine alpha sine theta. I apologize for that. I will, when I set out these slides, I'm going to fix them up so that they're free of errors. But using my polar coordinates, this guy was x, this guy's y, this guy's y, this guy right here is x, and so I can compact it into this formula based solely on x, y, and theta. And then, as an exercise, use the formula. Please prove that this is a linear transformation. The main thing I want to show is what is the matrix representation of this. So my standard basis of R2 is 1, 0, 0, 1. So let's see what happens to those points. If I plug it into the formula, I get 1, 0 goes to cosine sine, and then 0, 1 goes to negative sine cosine. So if I shove that into my matrix representation, and I'm just sending it from like the standard basis to itself, then my matrix representation will be, this is what happens to 1, 0. This is what happens to 0, 1. And so my matrix representation is cosine theta, negative sine theta, cosine theta. You can totally use the long form that we wrote before, but once we start talking about matrix multiplication, I can find my rotations by multiplying any vector by this matrix. And again, we'll talk about what that means in the next session. So, slowly wrapping up here, we saw before that for any set in any vector space, or any set to any field, if I do f of s to f, this forms a vector space structure. More generally, if I were to replace my field with a vector space, I also get a vector space structure by just defining it in the same way. So if I were to restrict this to linear transformations between two vector spaces, I also get a vector space structure. So as a proposition, if V and W are any vector spaces over a field F, then the set, I call it curly L from V to W, of linear transformations from V to W forms a vector space over F. And then instead of doing L of VV, if I have the same vector space, I write it as simply L of V. That is also a linear transformation or not linear transformation. This is also a theorem proven in Friedberg. I should have written that number down. It is theorem 2.7. I skipped over the part A, which is like A t plus u is also a linear transformation, but B really like says it. So knowing that, I can I can use that structure going on with my matrix representations. So how did that not get added in? So this is theorem 2.8. If I have two vector spaces with ordered bases b1, b2, respectively, I have two linear transformations, t1, t2, then I'm going to reduce this and write it down. The matrix representation of the sum is the sum of the matrix representations. I'm not going to do curlies because that'll look ugly with writing with a cursor. So the matrix representation of t1, t2 is the sum of the matrix representations of t1 and t2. And then if I multiply t1, or any linear transformation really, by a scalar, then the matrix representation of the scaled version is the scaled version of the matrix representation. So going into a quick proof of that, I'm going to write out explicitly what my bases are. B1 is a basis of V, B2 is a basis of W. So for every J in my first ordered basis, I can find unique linear scalars, A sub ij and B sub ij, such that if I apply it to T1, it's a linear combination of stuff in B2. If I apply it through B2, it's another linear combination of stuff in B2. So if I were to add these two together, I would get that the scalars add up like so. And if I look at the ith row, jth column, the entry of that would be the sum of those entries. This guy would be the ijth entry of T1. This would be the ijth entry of T2. I'm keeping that. This is the proof of the first claim from before. The second claim works in the exact same way. And just like in Friedberg, this is an exercise to the reader. And as my final slide for today, I love talking about linear transformations. And then whenever we have an assignment, it's a linear transformation. We just proved that we have a linear transformation going on between the vector space of linear transformations from V to W, and then the set of all M by N matrices with entries in my scalar field F. We just proved it preserves sums and it preserves scalar multiples, linear transformations. In our next section, we're going to prove that this is actually like a one-to-one correspondence, and this defines what we call an isomorphism. So really, when we're talking about linear transformations, we're talking about matrices, and these two are the exact same family. So we can do a lot of computational stuff when we live in our space of matrices here. I talked way too much. Questions, comments, concerns? Ooh, Andre had a thing. Can you show the statement of the theorem? Which theorem were you referring to? So I can go back to that one. 2 slides ago. This guy? Let me write this in full. So this theorem was just saying that matrix representations preserve sums in scalar multiples. Any final questions on just like anything I talked about today? I talked way too much. I want to hear from y'all. I want to clarify anything that I can, help extend anything. I know I went especially fast during the last time, but I also want to respect all y'all's time. Ooh. Can you post the Twitch question for me in the chat here so I can read and answer it?
Yeah, so I'll read it out loud. It's
Okay.
Serena was wondering. Well, first we had a really good discussion about where those rotation matrices live, and he was asking if they live in SL, the special linear group, and I believe they do because the determinant is 1.
Yeah, that's. I believe that Friedberg's going to get into that later, but yes, the determinant is 1, and it also which means like it preserves areas and it preserves orientation of the space. So I believe it does live in SL. And if I remember correctly, that if you live in SL, you can be thought of as a rotation matrix. I don't know that for a fact. I might just be talking out of my butt here, but I think that's the case. My knowledge of Lie groups kind of isn't really the best there.
Yeah, no, I'm the same way. It's been so long since I thought about them. And then the other question that Serena was wondering about, and I might be phrasing this incorrectly, so someone can correct me if I'm not stating this correctly. But Serena's asking, could you say that the set of linear transformations would be HOM functor from vector space to vector space, so homomorphic functor? And I don't know if you have the background for that. I'm not super familiar with functors, but if somebody is familiar,
I
that would be
know
helpful.
a little bit about category theory. I wish I had like a little bit more knowledge, and also it's been like a while since I've gone into this, but I believe you do have a functor going on from the category of vector spaces over a field F. I don't know what the category would be, but like, oh wait, no, it's also it's also over vector spaces over the field F, where you have 2 that are going on. I believe one is covariant and the other one's contravariant. I would have to like do a bit more thinking to think about which is which, but you have one where it's like you assign a vector space to to the vector space of linear transformations from V to W. Here, W would be fixed. And then you have another one which assigns it to the other spot. So you have one where it goes like V to linear transformations from, let's say, W to V. So you have one for the first argument, one for the second argument. This would definitely be more something to talk about in the next section, because then you would be talking about compositions. And really, when you have these functors, you would want to preserve compositions of maps. And that's really all like section like 2.3 and 2.4 are, because you're talking about isomorphisms, you're talking about matrix compositions of linear transformations, and that's when you're going to get into the matrix multiplication as well.
And Anders does say in Discord chat, Sereno, that Hom set the set of all homomorphisms in which in this case are the linear transformations. So I think verifying your claim is true, Sereno.
So when this is a little bit above where we're going, but this is helpful when you're extending to like abstract algebra, topology, really like anything where you have a structure. Here we have a set of objects that we care about, which is our vector spaces, and then we have a set of like homomorphisms, or like what we call functions, that we care about, in this case, which are linear transformations. We have to talk a little bit more about composition in order to really talk about categories like that, and then that's again in the next section. But yes, like our sets, our homomorphisms are these linear transformations that we care about.
Cool. So let us know if that helps answer your original question, Serena.
I had to put my money.
I was going to say, otherwise, I just wanted to say thank you very much for a lovely presentation. That you're very well spoken, and I think you delivered all of the major important concepts very, very cleanly and very well. So thank you again for that.
Thank you.
Thank you very much. It was awesome presentation.
This was very fun to do. Thank y'all for having me. Please remind me next time to have a glass of water when I'm doing this, because talking for 2 hours straight kills me.
Yeah, for sure. And then we have put a call out for presentations for January. If you're willing to pick up one of those in January or February, if your time allows for it, we'd love to have you back as well.
I'd be more than happy to come back. I just have to figure out like what would I want to do. Linear algebra is so cool. I really love this subject. This was really like one of my first introductions to like the idea of abstraction in mathematics and being able to be powerful. We like with that one example that I was ranting on with for a while on addition being multiplication, multiplication being exponentiation. Really like a lot of these things are under the same bubble, and being able to like have this power of talking about everything in a unified language is just really cool to me. And I feel like linear algebra helps bridge the gap through an idea of like geometric ideology in play with like, while still maintaining this idea of just like what happens when we go further beyond.
Yeah, totally. Getting a couple people like Fem, Peach, saying thank you from Twitch. And we have a linear algebra is so underrated as well, which I appreciate that comment.
But that, on the other hand, if from every like mathematician that I've talked to, you can never escape linear algebra if you're ever going into higher levels of math, because there's always something that pops up that produces some sort of linear algebra idea or something like connected towards it. Like linear algebra is such like an important field of study that like there's a reason why so much of it is covered and why so much of it is like still used like kind of everywhere we go.
Yeah, very true. So you had a couple slides in there where you kind of had left some stuff for us to think about as the reader. What I'll try to do is when you update your slides and post them for us, I'll try to grab those particular slides and post them into the problems forum so that we can have a bit more of a discussion on some of those interesting examples that you provided for us.
Yeah, perfect. Yeah, perfect. I'll try to get slides uploaded and updated by tonight.
Okay, sounds great. I'm gonna go ahead and just deafen on Discord for now so I can sign off on Twitch. But I'll be back in case anyone wants to debrief anything after I shut the stream down.
Perfect. Thank you so much, everybody over on Twitch. I hope you enjoyed. And yeah.
Awesome. So thank you everyone for coming and sticking around on Twitch. Mad shout outs to Gumboy again for an awesome presentation. To me, really kind of like threading a really fun discussion and story through linear transformation. So I'm super excited to see how this is going to pick up when we come back next time in January. So this is our last presentation for December. We're going to be taking next week off and then picking back up on January the 4th. And I believe Clonade's going to be back with us on the 4th of January. And then I've put a call out for people that are interested in presenting for linear algebra. So we're going to start kind of tying up the rest of January here as well. So as always, thanks very much for coming and hanging out. We're going to sign out, and then I'll be returning back to Discord for some discussions over there. So thanks again, guys. When is the next time I see you? I am taking a couple weeks off, so I probably won't see you unless I'm doing some gaming until January the 4th. So just kind of be mindful of that. I needed to kind of refresh my batteries here over the holidays. So we'll definitely be back doing math on the 4th of January, and maybe some gaming streams next week, but it'll be pretty chill. So you can find me in Discord in the meantime. All right, take care, guys.